Welcome guys, hope you're doing fine, enjoying my videos. And as you can see here, here's a revised problem of the question given in the previous video. So all I did was I removed a line that asks the side lengths of the triangle KBQ given over here. I removed it because I thought it would be very easy to find considering this statement was given. And along with everything else. So let's finally see the solution to that question today. So here's a diagram. We have a triangle ABC, and these are the circles. And then here, the first thing we want to do is find the radius of each circle, and then use trigonometry and then some theorems to figure out what kind of triangle ABC could be. So first, we reflect the figure ABC on this line. So I have like a tangential quadrilateral, and if the area of ABC is delta, then the area of the quadrilateral will be 2 delta, obviously. And then we use, well, the area divided by the semiperimeter gives the in radius for any tangential quadrilateral. Because if you take the center and then draw perpendiculars to each side, and then use area, like you basically take the side, let's call this side C, this side is A, and this side is B. So this is C, right? So C into the in radius divided by 2 will give the area of that triangle, and basically repeat it for every other triangle like that, and then that gives you the value of the in radius. So from that you'd get 2 delta as the area, and then the semiperimeter will just be C plus A. So basically have 2 delta divided by C plus A for the radius of this circle. Now, since A lies on the radical axis, basically the radical axis is the line of which from any point on that line, the tangents to each of these circles will be equal. And for 2 intersecting circles, it's just the line of which the common chord is a part of, is the common chord, right? So that's basically the radical axis. So the tangents from A are equal. So what's the tangent from A to this circle? It's basically just this radius into cot A, right? Because there's a right angle at the tangent. So that's basically what we do. And then we equate the tangents of both sides. Let's see how that's done. So here we have 2 delta cot A by A plus B is equal to 2 delta cot A by C plus A. Basically, we just use symmetry to find the radius of the circle. It's pretty much the same process. And now that we have B is not equal to C, because in the question it was given that it was a scalene triangle, we have A plus B is not equal to C plus A, and 2 delta just cancels out because it can never be 0. It's only 0 for a non-degenerate triangle, which we're not working with. So the only possibility is when cot A is 0. And cot A is 0 when cos A is 0, which happens only when A is 90 degrees. So basically, ABC is a right angle triangle. It's kind of annoying to know that this point just coincides or degenerates to this point. But we basically have cot B is equal to, cot B will be equal to C by B, and cot C will be equal to B by C. Now, since this is a radius and this is angle B, we find the length of this length, find the length of this segment, and then we use the same idea to find the length of this segment, and then we add them up to find the length of this segment, which is xy according to the question. So here we have BC by A plus B in a cot B. Basically we just substituted this thing. Also, the area of the triangle will just be half in a B and a C, so we have 2 delta is equal to BC. And then from this we get BC minus XY is equal to C squared by A plus B plus B squared by A plus C. Now A is basically root B squared plus C squared, so we just rationalize, we basically multiply by root B squared plus C squared minus B on both sides of this fraction. And then C squared cancels out with the product you get, the denominator, which also happens to be C squared. So you're left with what we call A minus B. that's basically the same thing we do here, and we get a minus c. And then bc minus this will just be xy. So we have b plus c minus a is equal to xy. Now for a right angle triangle, the in radius will just be the length of the tangent to the in circle from the right angle. And that basically just happens to be this side by this side plus this side minus this side by 2 for any triangle. You can try that out. It's just 3 simple equations which you have to solve, because tangents from a single point are equal to a single circle. That's all you need to use. So basically I have xy is 2r. Now we're calling this point O, the midpoint of this. So now we want the length of BO because we need to find something. Now BO will just be BY plus half of, well, XY, right? Because XY is just 2 times XO, that's all we need. So basically we have this, and then BY we just substitute the values. So I have A minus B is BY, and then half XY is just this, right? We just substitute this, and then that gives us this length. Now notice that we're adding these 2 sides and subtracting this side. So that gives you the length of the tangent from this side, which also happens to be the length of BO. That means O is the point of tangency of the incircle with BC, right? Because BO is equal to the length of the tangent from B to the incircle. So therefore we have sigma and omega. Those are the names of the circles given in the question. So these are 2 congruent circles passing through each other's centers. So let's see how the arrangement looks like. It's like this. So there's a line passing through L, and this is K, this is O, this is I. I'll explain why this is 60 degrees, by the way. So first, this is the radius of, well, this circle, and this is the radius of this circle. One of them is the incircle. This is the incircle, and this is the circle we're talking about. So this is R, and this is also R, obviously, because, well, OI is just the radius of both circles. And this is also R, obviously. So we basically have a nice equilateral triangle with angle 60 degrees. So this forms a nice rhombus over here. So yeah, OLIK is a rhombus. And therefore this angle will be 120 degrees because it's just symmetric. This will just be 60 degrees, and then both of these will be 120. Now since this is 120 degrees, any point over here, let's say there's a point P. So LPK will also be half of 120, which is 60 degrees. Also, you can also use you can derive this in another way. Like LIK is 120 degrees. So since LPKI is a cyclic quadrilateral, LPK has to be 60 degrees because it's 180 minus 120, which is 60. So that's why K, so yeah, we have K, and this is supposed to be point P or Q. So yeah, this is also supposed to be 60 degrees, right? Because angle in a segment is always equal. That's one important theorem for any circle. So this is 60 degrees, and by symmetry, since this is the same circle and this is the same common chord, this will also subtend 60 degrees over here. And this is a straight line. So we have 60 degrees, so this will also be 60 degrees, and we're left with an equilateral triangle. So that's basically all you had to do. And for the collinearity, this is also pretty easy. Well, one thing you can do is just coordinate geometry. Like you can just find the length of this, and then you can basically use coordinates, like take this as the origin and do stuff. It's pretty easy. I recommend you try this out on your own. So that's it for today. Hope you enjoyed the video. Thank you so much. Subscribe for more such content, and meet you in the next video. Thank you.